So, how do you even begin to create a blueprint for the human mind? I mean, how do you map out something so complex it can dream up a symphony, contemplate the universe, or just, figure out what a friend is feeling? It sounds kind of impossible, right?
Well, think about it. Every single second, your brain is basically performing little miracles of computation. It's turning light patterns into faces you recognize, sound waves into words you understand, and simple intentions into complex actions. To even start to tackle this, we need a framework, a set of tools. And one of the most powerful tools we've got comes from the brilliant cognitive scientist David Marr.
Marr had this amazing idea. He said that to really understand a complex system like the brain, you have to look at it from three different levels. Think of them like different zoom lenses. For this explainer, we're going to zero in on the first two, the what and the how, because the tension between them, well, it reveals something truly profound about how our minds actually work. Let's start at the very top. Okay, let's dive right in. The first level is what Marr called the computational level. Now, what this means is, before we even think about a single neuron firing or a line of code, we have to take a huge step back and ask a really basic but super important question. What's the problem the brain is actually trying to solve here? See, this level isn't about the nuts and bolts. Not yet, anyway. It's all about the objective. Think about a navigation app on your phone. The computational problem is crystal clear. Find the fastest route from point A to point B. That's it. It doesn't care how the app figures it out, it just defines the ultimate goal of the whole shebang. And what's so cool about this is how widely it applies. This isn't just for one little corner of cognition. At this computational level, we can define the problem of vision as, say, building a 3D world from the 2D images hitting our eyes. We can define the problem of guessing a friend's intention as just figuring out their goal based on their actions. It's always the essential first step.
Okay, so let's move down to the next level and see how this all connects. If the computational level was all about defining the what, the problem, then this second level, the algorithmic level, is all about the how.
Right, so this is where we get into the actual strategy, the recipe for solving the problem. Let's go back to our navigation app. We know the what is to find the fastest route. But the how, well, that's the specific algorithm it uses. Is it using something like Dijkstra's algorithm where it checks every possible path? Or is it using an A-star search to be a little smarter and more efficient? That choice, that step-by-step process, that's the algorithmic question. So here's the crucial distinction laid out, right? The computational level defines the destination. It asks, why is the system even doing this? The algorithmic level, on the other hand, describes the actual route you're taking to get there. It asks, how step-by-step does it pull that off? Now, this all seems wonderfully neat and tidy. You've got the what and you've got the how. But here's where things get really, really interesting. Right where the perfect theory crashes into messy reality. What happens when the perfect solution just can't be run on a finite biological brain like ours? This brings us face to face with what's called the intractability problem. Sometimes, a computational theory will describe the absolute, mathematically perfect best way to solve a problem. But there's a catch. That perfect solution might be intractable, which is just a fancy way of saying it would take a real brain an insane amount of time, like maybe billions of years, to actually compute it. The theory is beautiful, but our biology just can't keep up. And this puts scientists at a fascinating crossroads. When you hit this wall, you've really got two options. Option one, you can change the how. You can say, okay, maybe the brain doesn't use the perfect algorithm. Maybe it uses a heuristic, a mental shortcut, a good enough rule of thumb. Or option two, and this is a big one, you go all the way back to the top and you revise the what. You realize, wait a minute, maybe I defined the original problem all wrong to begin with. And that dilemma, that choice, it forces us toward a really critical insight. It's an insight about the true goal here, modeling how we actually think, not how some perfect imaginary machine might do it. Let's just pause on this for a second. What this quote is really saying is that we humans almost never use the perfect, optimal solution. Our thinking is full of these kind of messy, practical shortcuts that are incredibly effective at getting the job done in the real world, even if they don't look perfect on paper. And that right there is the core takeaway. For scientists trying to model the human mind, the real prize isn't finding the solution that looks best to a supercomputer. The prize is finding the solution that works best for the hardware we're actually running, our own biological brains. We're searching for what's cognitively optimal, not just mathematically perfect.
And this is exactly why Marr's framework is so powerful. You can't just stick to one level of analysis and call it a day. The computational what defines the problem, sure, but it's the algorithmic how that reveals the actual, clever, sometimes messy path that we humans take to solve it. To get the complete picture, you absolutely have to have both.
So I'll leave you with this final thought to chew on. We often think of our mental shortcuts, our little biases and glitches, as bugs, as flaws in our thinking. But what if they're not bugs at all? What if these supposedly imperfect solutions are actually the core features of an incredibly efficient, adaptable, biological intelligence? Rethinking that might just change how we define what it really means to be smart.